Alright, so continuing from the last lecture, we are essentially trying to investigate the retardation effect, right, or the speed of light delay effect of transmission lines. And to recall what a transmission line is, if I have a sinusoidally varying voltage or perhaps any other time varying voltage where the time rate of change of these voltages are rapid, right, we notice that these changes in voltages don't quite reflect at all positions of the circuit instantaneously. Okay, so this pair of wires is what we call as a transmission line. Right. So the transmission line essentially carries both the onward current and the return current. The onward current is the current going to the load. Let's call this RL for simplicity. It's simply depicted as a resistor, and then we have the return current going through the same transmission line and returning back to the source, right. So the retardation effect is saying that if I were to momentarily change the voltage at point A, I don't expect the same change at point A to reflect at point B instantaneously, but should rather take some time, right. This is the observed behavior. So we'd like to somehow model this transmission line, which is just a pair of wires. Before we jump into the more rigorous mathematics that I promised we'll do today, I just wanted to show you that when I have these transmission lines, right, I can either consider just a pair of wires, right, conducting wires, or like in the case that I showed in the last class, a coaxial cable where there is a central conductor and a return conductor surrounding it, right. So remember that the way we approached modeling this was to make some observations and saying that we would perhaps need resistors, capacitors and inductors in their ideal form to model certain aspects, right. So for example, the separation between the conductors could necessitate a capacitance, right, and the flux created by the magnetic field lines crisscrossing the area between the two conductors would necessitate an inductor, right. But just to make sure that we are clear on where the fields are persistent, right. So the electric and magnetic fields in an arrangement either shown on the case where there's two parallel conductors or the coaxial line, I expect the electric field to be present predominantly between the lines, right. And in the case of the coaxial line, I expect it to be radially oriented, right. So the field is mostly present between the conductors, right. This is similar in argument to the parallel plate capacitor model, right, where we showed that the fields add together, right, between the plates, whereas outside the plates the orientation of the fields from the individual conductors are opposite in direction. So I don't expect too much of electric field strength, right, to be present outside the pair of conductors. Similar argument can also be made to the case of magnetic field lines, right? So I expect from the right hand thumb rule the fields, magnetic fields generated from a current carrying conductor to the left would go into the page, right? And similarly from the top conductor also goes into the page between the two conductors, right? Whereas if you observe what happens outside, so let's say everything that's in red is due to the conductor at the bottom, and green is to associate fields from the conductor on the top carrying current to the right, right? So you can see that in the regions outside the pair of conductors, the field strengths are opposite in direction, so they would have a cancelling effect, right? So similarly, in the case of the coaxial line, I expect the field lines to predominantly be between the two conductors, right? So this is just to give you an insight into where exactly the fields exist, right? So outside of the pair of these conductors, you usually don't expect to see very strong electric and magnetic fields, okay? So in the last class, we came up with a toy model for a lossless transmission line. So we removed all the resistors and we said that just to invoke the effects of the electric and magnetic fields around these pair of conductors, we simply looked at just an LC circuit as an equivalent for a very small section of the transmission line, where we say that this section is so small that we are able to establish voltage current relationships instantaneously across the ends of these sections, and we were able to derive a set of conditions for the current and voltages in this pair of conductors. We call them telegraph equations, and this is for the first time where we introduced a spatial variation in voltage and current, okay? Now voltage and current are now functions of two independent variables, right? So this is the first step in understanding from your high school, right? So these functions already, I can say, are starting to get a bit more complicated, right? So before, the voltage was only a function of time, and now we are allowing it to be both a function of space and time, right? But the reason to keep it to transmission lines as an example is to still keep the complexity, right? So out of the three dimensions, we are only keeping one of the dimensions, right? Nevertheless, I still feel that this already introduces a large amount of richness in the subject, right? But as we discussed at the end of last lecture, the notion of these inductors and capacitors was a bit ad hoc, right? So we just made some observations based on the physical construction of this cable, and I said that we will take a look at this from the Maxwell's equations point of view and see that only a single and an L and a single C is sufficient, right, to basically map out these fields through circuit elements, and that there would not be any more complicated circuits that we need to come up with. Okay. So, in order to derive the first of the telegraph's equations, we will consider the coaxial cable. Okay. And we will take a contour okay, which is like a cylindrical shell around the inner conductor with a very small slit, right, and the edge of this cylindrical shell, right, can be considered as our contour, right. So, I go clockwise and then along the cylindrical surface, I am going all along the edges, right, and then I would be coming backwards and then completing the loop. Okay. So, just think of taking a straw, right, and then having the central conductor going through the straw, and this straw basically has a very fine slit, right, and I am basically considering the line integral along the edges of this straw, right, or this structure. Okay, so remember that the magnetic field lines are essentially wrapping around the central conductor, right. So, let us write our Ampere Maxwell equation, where we have so this is sort of an isometric view. Maybe another view that I can draw is one looking at the cable from the side. This straw has a certain length, okay, and we'll call this length delta x, right. So, this is x and this would be x plus delta x. Okay, this is just the same diagram in the top, but drawn with a little different perspective, right. So, now at x, right, so we have a B field at x, right. So, we are looking at B at x dot ds okay. So if the current going through the central conductor is from left to right, remember that the contour here, right, I am going along the B field, right. So this integral would be positive, right, because ds, the small line element within the contour, is aligned with the B field vector, right. So this contour that I go around the central conductor on the left hand side at x will be positive, right, whereas at x plus delta x it would be negative, because I am moving in the opposite direction to the orientation of the magnetic field, right. So B and ds are 180 degrees out of phase, so it will be negative, right. So we have integral B at x plus delta x dot ds. Okay. So what is the right hand side? Remember that there can be some steady currents, right? We are not interested in steady currents for now. There could be steady currents going across, but nevertheless the difference of these two would disappear, right? If there is a steady current, then essentially this integral, the left hand side would vanish for any steady currents, right? So this will only be a non-zero value if I have changing electric fields. Okay, so this is the Ampere Maxwell equation. So locally at x, right, so I can say that the first term on the left hand side is quite simply mu 0 times I at x, right, and the second term would simply be mu 0 times I at x plus delta x. Okay, and for the right hand side we actually have to invoke Gauss's law, right. So this is a surface now, it's a closed surface shown by the straw example. It would be basically the surface of the straw, right, wherever you see plastic. So this would essentially be Q enclosed by epsilon naught, right. So this small region between x and x plus delta x would hold some time rate of change of charge, right, and that is essentially what this flux is, right. This is essentially from the fact that this slit is extremely small, right. The slit is so that it is the two lines going back and forth, right. The two lines that you see going back and forth are very close to each other. The slit is infinitesimally small, right. So more or less I am having a wrapped situation. So all the field lines that are coming from the central conductor terminating at the outer conductor or vice versa should be generated due to charges within this enclosed structure, right? Alright, so now we can proceed by removing mu naught from both sides. So I have Ix minus I of x plus delta x is equal to, and the epsilon 0 also cancels, we have dou by dou t of, here we are going to say it is c times delta x. So remember that L, C, R and G now have units that are the conventional units per unit length, right? So C here stands for capacitance per unit length of my transmission line. So in order to get the capacitance for the region between x and x plus delta x, I should actually multiply the capacitance per unit length by delta x to get this net capacity for this small section times the voltage, right? Let's say voltage at x. You can also consider that this is a mean voltage of x and x plus delta x, doesn't matter, right? So the c times delta x is not a time varying quantity, so I can pull it out and I can take the delta x to the left hand side. So I have Ix minus I of x plus delta x divided by delta x is c times dou v by dou t, right? The left hand side, the limit of delta x becoming small is essentially minus dou I by dou x. Okay, so this is more of a rigorous derivation for one of the telegraph's equations, right? So rather than just making hunches that I might need a capacitor for two conductors that are separated by a distance apart, or I might need an inductor for the flux lines created, right, between the two conductors. Here is more from a field standpoint, right, that we are able to get the same relationship that we derived, right, using the estimated model. Okay, so this is all, of course, stemming from the fact that we already know how the field lines are oriented between the conductors. Nevertheless, I think showing that there is always situations that obey Maxwell's equations is a very confirming way, right? It gives us a lot of confidence that perhaps there is no other elements that are necessary. I don't need another capacitor in parallel or something like that, right? So the capacitor in the model is essentially mapping, right, the fluctuations in the electrical flux between the conductors and its impact on the currents, right? So remember that this is something that we didn't have in the toy capacitor and toy inductor model, but for the transmission line treatment to invoke the retardation effect, it is essential that we have this Maxwell's added term, right, which is time rate of change of electrical flux creating magnetic fields, right, which gives us one of the telegraph's equations. So now we'll derive the second telegraph's equation. Where we need to invoke the magnetic field, rate of change of magnetic fields, right? So here again I take a small segment x to x plus delta x, and then I create a contour. Okay, let me call these points A, B, C and D. Okay, so I create a contour, a rectangular contour between the two conductors, right? And I am going to essentially invoke Faraday's equation. Okay, Faraday's law. So the closed loop integral of E dot ds along this contour, where the contour I can describe by saying it is A, B, C, D, A. Okay. Now this is the negative. Remember, the negative sign came from Dr. Lenz, right? To say that the generated electric field tries to create magnetic field that opposes the original magnetic field, right? So that opposition is what is being mimicked by this negative sign. What is this integral closed loop surface integral B dot dA? Okay, this is the surface enclosed by ABCD, the rectangle, right? This B dot dA is essentially your magnetic flux. Okay, the magnetic flux, let's call it phi, we said was, sorry, yes, to be clear, we can just the product B dot dA, that's what I mean by magnetic flux. We said was L times I, right? But remember that L is inductance per unit length. So in order to get the inductance, the self-inductance between the pair of conductors for a short length delta x is L delta x times the current flowing. Alright. So this E dot ds on the left hand side. So remember, for the pair of conductors, the electric field is emanating from the central conductor and reaching the return conductor. So for line integrals from A to B and C to D, this should be 0. Why? Because E and the ds, which is the line element along the contour, are perpendicular to each other, right? So I have my electric field in this direction and my ds element along the contour, right? So these two are perpendicular to each other for the line segments AB and CD. So I only need to consider the integrals from B to C and D to A. Alright. So I'll call this B to C E dot ds. Remember, this is electric field at x plus delta x, right? And of course, E and ds are in opposing directions when I go from D to A. So I have a minus sign now. Actually, since I have adopted the minus sign, I can just say A to D. This is electric field at x times ds. Alright. So this is minus dou by dou t of so the total magnetic flux is L times delta x times I. Okay. But what can you say about this? This is simply the voltage drop, right? So the voltage drop at x plus delta x minus the voltage drop at x is minus of dou I by dou t times L delta x, right? So again I can bring the delta x over to this side, which gives me dou v by dou x is minus L dou I by dou t. So this is our second telegraph's equation. Okay, so we essentially invoked both the Faraday's law as well as the Ampere Maxwell equation in order to arrive at the two equations called the telegraph equations for transmission lines. Okay, so whether you're comfortable with starting from the mathematical Maxwell's equations and arriving at the telegraph equations, or perhaps going the route which we did in the last class, which is to look at the construction of the transmission line and noticing where the electric fields are and the orientation of these conductors, we may basically try to find equivalent ideal circuit elements to capture different effects, right? So whether we go either way, we are getting the same set of telegraphs equations, which is a comfort, right, that we can have.